Hey y'all, today we're going to be asking the question, will a precipitate form? And we're going to look at a couple of different scenarios in which we will be asking that exact question. Essentially, it is going to take an application of Q versus K to be able to determine the answer. So let's go ahead and get started and take a look at how we're going to do it. When we're looking at whether a precipitate forms as it pertains to Q and K, we need to remember that the equilibrium expression KSP is set up so that the products are the ions and the reactant is the solid. If we remember back to general equilibrium, if Q is less than K, we favor our products. Now the products are the ions, which means any solid will dissociate into ions if Q is less than K. This means no precipitate would be forming. If Q is equal to K, we are at equilibrium. So there's no net formation of a precipitate. And then when Q is greater than K, we're shifting our entire process to favor the reactants, which is the solid. So when Q is greater than K, we are in fact going to form a precipitate. So this is the Q versus K comparison that you're going to be required to make during problems like this. Let's go ahead and get started with a practice problem. We're going to have a situation here where I'm combining two different soluble compounds, lead 2 nitrate and sodium sulfate. When I combine these two, we are going to predict an insoluble product, lead 2 sulfate. However, the question is, will there be enough of the lead 2 sulfate to cause a precipitate to form? Will we create a solution which is saturated with lead 2 sulfate? So let's look at how we're going to attack this. First, write the equilibrium expression. KSP of the thing that is going to be potentially precipitating, in this case, the lead 2 sulfate. Once we do that, we see that we have a KSP equals the concentration of lead 2 plus times the concentration of sulfate 2 minus. One thing to keep in mind is that when we are doing any of these problems, the spectators can be ignored. So the sulfate ion matters, the lead 2 plus ion matters, but the sodium ion and the nitrate ion, they're spectators, so we ignore them, all right? And as a result, we can just go ahead and solve with just the lead 2 plus ion and the sulfate ion compared. Before we can plug into our equilibrium expression, we need the new concentrations of both my lead 2 plus and sulfate ions. When we take two volumes in atom together, I have to make sure I account for that changing volume. That means I'm going to use M1V1 equals M2V2 as a dilution to find my new concentrations of both lead 2 plus and sulfate. I take the concentration of the lead 2 plus ion that I added, multiply it by its volume, and divide by the total volume. Remember, the total volume in this case is going to be 0.5 because I added a 0.1 and a 0.4 liter solution. I do the same thing with the sulfate ion. So I need to find the number of moles of sulfate ion that I added, then divide by the 0.5 liter total volume. This gives me my new concentrations, where lead's concentration is 1.3 times 10 to the negative 6th moles per liter, and sulfate's concentration is 4.0 times 10 to the negative 3 moles per liter. I'm taking those values and plugging them into my equilibrium expression, my mass action law, to solve for Q. When I do, I see that the Q value is 6.4 times 10 to the negative 6th. I compare this to my K, and I can see that in fact Q is greater than K. As a result, our entire equilibrium will shift to favor the solid, the reactant, and a precipitate will form. This tells me that the solution that I created by combining these two reactants in fact created a saturated solution, and any excess began to precipitate out. All right, so how about you try one? I'm going to combine two solutions here. We have barium chloride and silver nitrate, and we're combining them together. So I want you to solve this and determine, will a precipitate form? Once you do, come back and we'll explain together. So what'd you get? Did a precipitate form? Well, the answer is no. Let's talk about why. When silver chloride comes together in this process, we need to find the new concentrations of silver ions and chloride ions. All of these are going to get put into our mass action law, our KSP expression, but we're solving for Q. So the silver and the chloride are at a 1-to-1 ratio. And in order to solve for my Q, I'm going to multiply the concentration of silver times the concentration of chloride. That means I need the concentration of silver and I need the concentration of chloride. The concentration of silver is going to equal the volume of silver ions that I added times their concentration divided by the total volume. Total volume is now 150 milliliters. So after the dilution, what I have here is a total molarity of 5.0 times 10 to the negative 6 moles per liter of silver. Be careful with this chloride ion concentration because barium chloride is BaCl2. We need to make sure we're multiplying the number of moles of chlorine by 2. So in other words, it's going to be 2 times the molarity of barium chloride to get the concentration of chloride itself. I'm going to end up with a concentration of chloride ions of 2.7 times 10 to the negative 5th moles per liter. I plug those values into my equilibrium expression to solve for Q. Q is equal to 1.4 times 10 to the negative 10th, which is smaller than the K value. And as a result, the entire reaction would shift its equilibrium towards the products, which are the ions, therefore no precipitate would form. So that wraps up today's video. Let's do a quick recap. Today we talked about how we could predict if a precipitate will form when we're combining 2 different solutions. Remember that we are looking specifically at a Q versus K comparison. If Q is greater than K, a precipitate will form. If Q is less than K, a precipitate will not form. One of the things to keep in mind is that you always need to find your Q value at the initial concentration. So whatever the new concentrations would be based off of the combination of volumes. If you're combining 2 things and you're combining their volumes, make sure you're using that new total volume in your calculations. That's one of the most common mistakes that's made here. Today's video was written, directed, edited, and produced by Jeffrey Pan and Sean Tao. Thank you all for watching. I hope you enjoyed it, and I'll see you in the next one.